Okay, so welcome everyone to today's One Word IAMP Mathematical Physics Seminar. This is a regular seminar series of IAMP, International Association of Mathematical Physics. And if you are watching this on YouTube, then you can click M intersection phi logo you see below, and click. If you click about, then you will learn more about this seminar series. Okay, so it is our great pleasure today to have Sinya Aoki, who is actually the director of Yukawa Institute for Theoretical Physics in Kyoto University. And Sinya is an expert in numerical approach to lattice QCD, and he's also a very good friend of mine. And as an old friend, I made an unreasonable demand for him to give an overview of Lattice QCD, and he kindly accepted. Thank you. So we are looking forward to your talk. So the floor is yours, Sinya.
Okay, thank you for introduction. And actually, it is my great honor to give a talk here, even though I'm not a mathematical physicist. And I was a little hesitated to give a talk here, but Hal convinced me I should give us some talk here. But I'm still a little bit afraid. My slide was too catchy, so please ask a question if you have any. So let me start my talk. Title of my talk is Lattice QCD, Introduction, Result, and Challenge. So first part is the introduction about Lattice QCD. So although you may know very well the atom made of nucleus, a nucleus made of protons and neutrons, and also proton made of quarks. And so question is how quarks becomes proton and neutrons or some others. So let me explain the QCD, although some of you know very well. QCD is a theory for dynamics of quarks and gluons. This is we may say it's a three-gauge theory. And you can also compare compare to the QED, quantum electrodynamics. And Lagrangian density of the QCD is given by this. It's quark part, quark, Q bar Q, and covariant derivative with gluon, and also gluon field strength squares. So quarks interact with the gluons, like this interaction and coupling G. And you can see this Q bar mu Q is made of, quark has 3 index, 1, 2, 3 for each. And we have the Lie algebra for SS gauge group here, TA, AB, and also gauge field has index A from 1 to 8. This is quark-gluon interaction, and it's very similar to the electron-photon interaction in QED. And field strength F mu nu is we can written in terms of A like this. And non-trivial part is we have a nonlinear term for a square in the field strength. Therefore, field strength square contains self-interaction, which is absent in QED. So we have 3-point gluon vertex, which has coupling G, and 4-point vertex, which has coupling G square. And this coupling must be equal to this coupling because of gauge invariance. So therefore, G is a unique coupling constant in QCD. And it's important, this is universal for all flavor of quarks and gluons. That is a very specific property of the QCD. So there are several properties of the QCD. One is asymptotic freedom. This means effective coupling become weaker at short distances. In terms of the lining coupling, G equals 0 is a UV fixed point or a Gaussian fixed point of the theory. And actually, Gross, Wilczek, Politzer got a Nobel Prize in order to show this property. On the other hand, at the infrared region, effective coupling becomes very strong. And that lead to the property so-called quark confinement. No isolated quark can be observed in nature. This may corresponding a possible IR fixed point exist at G infinity, but at this point we don't know there exists a IR fixed point or not. And this, because of this quark confinement, free proton means it's three quarks interacting with each other by exchanging a lot of gluons so that they move coherently like this. To understand this behavior, we need a non-perturbative method for QCD at low energy region. And that is a Lattice QCD. Sorry, do you know how to move this zoom bar from, oh, sorry. Yeah, sorry, yeah.
Okay. We don't see that, but.
Yeah, I cannot say my type. Okay, this is the Lattice field theory part. So important things is that this is a rigorous definition of quantum field theory, as you know, without using perturbative expansion. So first, we define the theory on ns times a cubed times nt times a Euclidean lattice with the lattice spacing a. Here, a is gives the UV cutoff, and this box size gives the IR cutoff. In this setup, this theory is equivalent to a quantum mechanics with finite degree of freedom. Therefore, this theory is well defined. That is very important. Then we have to take a continuum limit, a equals 0 limit, with box size fixed. Of course, if you are interested in the thermodynamic, if you are interested in the phase transition, like finite temperature phase transition, in that case, you have to take the thermodynamic limit before the continuum limit is required. However, if you are interested in the property of the hadrons, we usually consider the finite box and take a continuum limit. Of course, in this case, number of points becomes infinity, but box size is still finite. Then after the taken continuum limit, we can obtain Euclidean correlation function in QFT. Then, as you know very well, we can use Ostwalder-Schroeder theorem, and we can rotate it in the theory into the Minkowski space. So we can obtain Minkowski correlation function in QFT. Then we may use Weidmann reconstruction theorem and obtain Hamiltonian and vacuum of the theory. This is maybe the logic to obtain the QFT from the lattice field theory. And the lattice QCD is just defines QCD on a discrete spacetime, like this. So we have lattice spacing A, and the box size L is n times A, like this. So, and we put quarks on the lattice side, like this, Q and Q bar. And also we put gluon field on the link with U, but U is, you may think it's exponential of the link variable A mu. That is an element of the Lie algebra. So therefore it's a SU3 matrix. But in terms of gauge field, it contains the infinite number of field. So that is, in some sense, this is very non-perturbative field. And the U is defined from X on the link, X plus mu. And opposite direction is U minus mu, X plus mu becomes this direction of the dagger. So this is the rule of the arrow, like this. So we can compare continuum QCD, we have the covariant derivative like this, but from the lattice, we have covariant difference. So we have X and X plus mu and X minus mu, but to keep gauge invariance or to replace to represent covariant derivative, we put link variable here. So x plus mu, we have u, and x minus mu, we have u minus mu x. And if we consider this interaction, we have infinite number of gluon field interacting with quark field. So therefore, quark interact with many gluons in a very short time, like this. So we can write down the quark action with q and qx plus mu and x minus mu with link and mass turn. And this action is gauge invariant under this transformation, q field with q times omega. And q bar is omega dagger, and link variable is omega u omega dagger. And omega is again SU3 element. And this Fermi action, however, has a problem, so-called doubling problem, but we know how to deal with it. So therefore, I don't explain what is doubling and how to solve it. But please believe me, we know how to deal with the doubling problem. And for the gauge action, in the continuum case, is f mu nu square. But on the lattice, we have this squares. This square, we call this a bracket, x plus mu, like this. So we put product of 4 link variable, this link, and this link is this link dagger, and this link is this link dagger. Important point is this action is also gauge invariant if we take trace. And the gauge action is given by 1 over g square and this trace of this bracket. And of course, we can take other shape like rectangular or chair, is very complicated, or so-called parallelogram, etc. These actions are also okay as long as they are gauge invariant. In that sense, lattice gauge action is not unique. Also, Fermi action is, of course, not unique. So to quantize, we use path integral. So continuum QCD case, some expectation value of the operator O can be represented by path integral over gauge field and quark field. And usually we expand interaction part and calculate using free part. And that is just perturbative extension. However, in that case, we need gauge fixing. On the Lattice QCD, we integrate out link variable and quark field and some operator. But integration of the gauge field, we use Haar measure. Therefore, gauge fixing is not required thanks to this Haar measure for a compact group like SU3. And important property of important property of this gauge integral is if we have the one link variable and integrated over U becomes 0. That means gluon field is very random. But however, if we have U and U dagger, since it's SU3, it just gives 1, and we normalize integral. This is just identity, 1 3×3 matrix. And also, thanks to the SU3 nature, determinant of this integral is also gives 1. So this is a very simple rule. And we have maybe more complicated integral, 4 link, UU dagger, or maybe 6, or etc. So instead of perturbation theory, we can also do the strong coupling expansion in Lattice QCD case. So if we take G goes to infinity, we can neglect gauge action. Gauge action becomes 0. So gauge field is completely random. In this case, quark propagation, it's become 0 by U integral. So this represents quark confinement. However, if we have U and U dagger, which means mesons, meson can propagate because it becomes non-zero even after the U integral. Also, baryon, if we have 3U, because of the determinant, it becomes non-zero. Therefore, meson and baryon can propagate even in the strong coupling limit. So like this. So baryon can coherently move. But in terms of perturbation theory, it's very complicated diagram, which cannot be calculated analytically. If 1 over G is small but non-zero, we can have the correction. For example, for the baryons, one quark ring may propagate like this. But because of the 1 over G correction, we can put bracket here. Then U integral becomes non-zero, we can get 1 over G square correction. This is a strong coupling expansion. So 3 quark can propagate separately like this, but still coherently. And it becomes free baryon in terms of, quark field. But of course, we cannot calculate strong coupling expansion in infinitely many orders. Therefore, we have to use numerical technique, so-called Monte Carlo simulations. So we consider some, again, vacuum expectation value in the path integral like this, dq, q bar, du, and quark actions, we can just represent q bar, du, q, and gauge action, some operator. But since on a computer, we cannot deal with the Grassmann number, which are used to represent a quark field, we integrate of the quark field, which just gives the determinant. And also Q and Q bar can be replaced D inverse or some other field. So we have some complicated operator O hat, but it's just function of U and gauge action and determinant and only U integral. And as long as this PU means determinant DU and SGU is positive, we can regard this part as a probability distribution of U. And we can use so-called importance sampling according to this probability distribution. This is a Monte Carlo simulations. And in this talk,
so when you do this fermion integration, so do you do this on lattice setting, and is this an exact procedure?
Exact procedure, lattice setting.
So you can compute this O of U, whatever.
It's finite. It's just determinant of finite dimensional matrix.
Okay.
So it's very defined, no infinity at all. Although it's very large matrix, so it's very difficult.
Okay, thank you.
And using this technique, we can calculate very complicated QCD process by computer simulations. And I will not explain the algorithm or etc. because you may not so interested in these technical details, but it's now possible. However, of course, use of the supercomputer like Fugaku are required. And even using supercomputer, calculation are not so easy. And however, recently, Hadron mass has been calculated very accurately. It means free Hadron can be very accurately calculated. And also, if this operator du is some matrix, has small eigenvalue, calculation of determinant or calculation of D inverse becomes very time consuming. So now just finish the Lattice QCD part. Some questions? No?
I have a question. So this is QCD. What about the standard model where you have gamma 5? Can you?
Yeah, that's a good question. Actually, we cannot rigorously define chiral fermion on the lattice at this moment. Some people are now trying to put to try to define chiral fermion. Chiral means eigenvalue of gamma 5. We cannot keep that property on the lattice. Therefore, rigorously speaking, standard model cannot be defined at this moment. However, some people are not trying to put, and actually, I don't know, there is successful or not, but some people are now claim it might be possible, but it's very difficult.
Thank you.
Yeah, I have a question. Now you say the determinant is it always positive or
No, not always positive. It's, for example, if we consider only one quark, it's real but not positive definite. Therefore, we have two quarks at the same mass. In this case, it's real positive. However, if we, for example, if we have the finite chemical potential, determinant becomes complex. Then we cannot use Monte Carlo simulation. This is so-called sign problem, and this is a very big challenge for us to simulate QCD with finite chemical potential.
So that's still an issue.
Yes.
Yeah. So you have to assume that this determinant is in a regime.
So
where
we
this
can only consider positive real determinant case, and so we need some. And for only real case, sometimes possible, but still it's difficult.
Thank you.
Okay. Now let's explain how to calculate Hadron spectra on the lattice. So this is some complicated diagram. And for example, effective determinant in perturbation theory, it's have this diagram like gluon create quark and anti-quark and annihilate again and coming back to gluons like this. And to calculate Hadron mass, we calculate so-called two-point correlation function. So we generate proton at time 0 and annihilate proton at time t and point x and summed over x to make its zero momentum. And this is in terms of operator formalism, but we can calculate this by path integral. But to understand the physical meaning of this two-point function, we use operator formalism, and we put some identity in terms of field, state. So it's decomposition of the identity. So here n is the eigenstate of Lattice QCD, so-called Hamiltonian, but it's not Hamiltonian. Rigorously speaking, it's transfer matrix, eigenstate of the transfer matrix, but we usually call it Hamiltonian. And also, since it's Euclidean lattice, we don't have hermiticity. So instead of hermiticity, we have usually reflection positivity. However, reflection positivity is sufficient condition, so it's not necessary condition. So sometimes lattice action violate reflection positivity. And but we assume such an identity, decomposition of identity exists and insert in between. And using Heisenberg representation, this becomes exponential of some eigenvalue of the Hamiltonian with exponential minus mt. And since it's zero momentum, the eigenvalue becomes mass with some several different exponential. And the coefficient is just matrix element square of like this. So it's some of the exponential. Of course, we have plus some extra piece, which may be given by 2 particle or 3 particle or 4 particle state. But we are interested in 1 particle state like this. So it's a sum of the exponential. Therefore, if t is very large, other exponential is, can be neglected, we can obtain lowest exponential pieces. Then we can extract mass of the ground state hadrons from large T behavior. So this is directly from Euclidean correlation function. Therefore, once we obtain mass, we don't need to go to Minkowski space. So we just calculate this mass at some finite lattice spacing and take continuum limit. Then we can obtain hadron mass in the continuum limit. So this is some example. So if we consider Meson 2-point function, this is the time. So it's exponentially decaying. But since we use periodic boundary condition in time, so we also coming back like this. So it's because of periodic boundary condition, exponentially become Koch. And red one is low Meson, and the black one is pi mesons. So if you compare slope, pi meson slope is shallower. That means pi meson is lighter than low meson. For nucleon case, we have some exponential decay, but opposite one is not nucleon. It's parity partner of the nucleon. So it's N plus parity positive nucleon and parity negative nucleon. And slope is again, this is steeper, means nucleon is lighter than the negative parity partner. So we can calculate these things on some lattice spacing and obtain mass and take continuum limit or something like that. But first, we have to do so-called chiral extrapolation. As I said before, so it is difficult to make quark mass as small as experimental value in numerical simulation because of the small eigenvalue problem of the determinant or the inverse. Therefore, we calculate pion mass at heavy point and extrapolated that result from heavy quark to physical point. That is so-called we call chiral extrapolation. This is pion mass cases. So we have some pion mass. This is just lattice unit. So we get some number with different quark mass. So vertical lines represent some quark mass in terms of some parameter. And we expect this quark mass, pion mass go to 0. Sorry, this is the pion mass square. So pion mass square goes to 0 in the, some limit. So we call this is a chiral limit. So it's this point represent 0 quark mass. Then we can calculate nucleon mass, low meson mass, and extrapolate these mass to chiral limit. Or physical point is very close to this point. Very close to this point, we may get physical pion mass, 135 MeV. Then we can get physical low meson mass or physical nucleon mass.
Excuse me, why is it called chiral? There seems to be no chirality here.
Yeah, but at usually continuum QCD, we have if quark mass is 0, we have the so-called chiral symmetry. Even though it's vector-like, gauge interaction is vector-like, but still massless quark has chiral symmetry.
Okay, thank you.
Yeah.
So yeah,
but the problem is we cannot couple to different gauge field to left chiral mode and right chiral mode.
I see.
I also have a question. So
yeah.
Does it mean that you need to know at least one mass of one thing, like pion mass, and then in real world?
Yes.
So in this case, you can sort of compute the ratio between the mass of, say, proton.
Actually, we need two mass.
Two.
Because this, I will explain later, but this one pion mass fix quark mass, bare quark mass. But we also have to determine the lattice spacing, since everything between lattice is just number. We don't know it's MEB or GEB. We don't know at all. Therefore, for example, if we calculate low meson mass, some number, but we assume this low meson is physical value, then we can convert, we can determine lattice spacing. So we need two input. We have two parameter, gauge coupling constant and quark mass. We fix these two coupling by the input from experiment. Then we can predict nucleon mass in QCD.
Okay, and I also have a question about the previous part. So you told us that you can compute mass by looking at this decay e to the minus mt. But you're saying that you can compute mass of different particles. So that means you choose proper p bar for.
Yes, so if you use different operator, so they have different quantum number, like quark flavor or some parity or etc. Then we have different decay rate depending on quantum number. So we need some different quantum number. Yeah, you are right. So we have to take many different operator and calculate.
Okay.
But if we have same quantum number, it's difficult. We have to maybe calculate excited state like M1 or second excited M2 or etc. It's excited state which has same quantum number.
You can also calculate C0, C1. Do they have a physical meaning?
Sometimes physical meaning. It gives some matrix element, like vacuum to one nucleon transition matrix element by this operator. Yeah, if we can extract C0, we can calculate this quantity in principle. But sometimes not so easy, but it's possible.
Excuse me, I have a question about your plots for the nucleon propagator. Why is it not symmetric with respect to the time? I mean, not periodic with respect to time?
Oh, because periodicity flip also positive energy part to negative energy part. The periodicity it's related to the charge conjugation or something like that. So if we take up component for the proton and plus, and the coming back is a parity opposite state. But if we take three or four component of the Dirac spinor, we can get n plus. Yeah.
I see.
So because of the spinor indices.
Yeah. Okay. Thank you.
Okay. So then we can calculate.
Okay. Excuse me. Sorry. And let me just ask one more thing. I may have missed, but why is this graph linear? For example, the left graph. I mean, 1 over k versus the mass.
Very small quark mass. If pion is a Nunn-Goldstone mode of the chiral symmetry breaking, the order identity predict its proportion to linear. I'll explain. Also, we have the correction.
I see. Okay, thank you.
Related to the spontaneous symmetry break of the chiral symmetry. However, in this calculation, chiral symmetry is explicitly broken because we have to remove so-called doubling problem. Then chiral symmetry is not exact on the lattice, but therefore there's some other reason why it looks like linear. It's like a critical exponent of the correlation function of the Ising model. So it's 4 dimension. It's almost mean field. It's 1/2. So square is just 1. So it's linear. So it's like mean field behavior of the phase transition.
Okay, thank you.
It's just my master paper. You may remember. Okay, then once we can, as I said, we have two put, but one is prediction. So we get nuclear mass in the physical unit at some lattice spacing. Then we have to take continuum extrapolation. A goes to zero limit should be taken. So this is some example. We have some lattice spacing and some nuclear mass. It's in terms of GeV. So it's maybe 4 point. And we take linear, some extrapolation. One is simple linear extrapolation. We get this number. But of course, we may have a square correction next reading of the term. That extrapolation gives this curve. So we can always fight with this kind of ambiguity in the actual simulation. So, but this is just example. So there are several remarks. And simulation at physical quark mass, that means pion mass is 140 MeV, become possible thanks to the improvement on both algorithms and computers. And also the leading discretization error is for gauge action, it's a square with some possible logarithmic correction like log NA. So n from 0 to some finite, maybe many infinite numbers. And also for quark action, correction is A times log again. And of course, we may improve the leading discretization error by changing, for example, lattice quark action, and that can make it A square or something like that. But because of this log term, there is no theoretical formula for the continuum extrapolation. Previously, I assume there is no log behavior, so just consider polynomial in A. But rigorously speaking, we have A log A or A log A log square or etc. And the quark mass dependence, however, is controlled by chiral perturbation theory if quark mass is small, but not for all Hadron mass. For example, pion mass, we can have so-called chiral perturbation theory. And the chiral perturbation theory predicts pion mass square linear in MQ plus correction MQ times log MQ, and also polynomial in MQ like this. Of course, we have higher order, more higher order. And such an example you can find, you can see this one. So this is quark mass, this is pion mass square divided by MQ. So leading order, it must be constant. However, because of this correction, we have some curvature. And actually constant to be appear at this point, not this point. So fit is not so easy in that such a situation. But important point is we have some theoretical guideline to take chiral extrapolation like this. And fourth point is recent trend is people calculate observed like Hadron mass at various volume, quark mass, and lattice spacing, and perform simultaneous fit for volume, quark mass, and A dependence. Not previously, I first make chiral extrapolation, then continuum extrapolation. But instead, they just fit one functional form, very complicated functional form, but take both chiral and continuum extrapolation. So this is one example by BMW collaboration. Sorry. So this is nucleon or some other hadron omega mass. So they make calculation at 3 lattice spacing. So blue, green, red, and various quark mass or pion mass. This pion mass divided by some other hadron mass, it's dimensionless quantity. So they fitted these data, but you may see some several lines, like dotted line, solid line, or maybe dashed line. And they assume some functional form and extrapolate to the physical pion mass and A equals 0 limit. Or similar things is dimensionful quantity. This current recent trend. But I'm a little bit worried about such a fit because this depends on the assumption of your functional form. But so far people using this kind of simultaneous fit. But as you can see, A dependence is very, very, very small. So maybe okay. So this is a state-of-art result of the Hadron mass, but it's already 2008. And we have many particles. So you may not familiar with name of the particle. So I'd like to explain. So baryons made of 3 quarks. Up and down quark, we have nucleons, a proton and neutrons. In this case, it's so-called octet baryon, spin 1/2, or decoupled baryon, spin 3/2. So octet baryon, we have only proton and neutron, but decoupled baryon, we have so-called delta plus plus, plus minus 0. And we have also contain strange quark, S quark. So we have sigma. If we contain 1 strange quark, we have sigma or lambda. And also if we have 2 strange quark, we have Gz. For octet cases, corresponding to one is sigma star or Gz star, and also omega, which made of 3 strange quarks. And for mesons, we have pion from up and down quark, and also vector meson is rho meson. Sorry, pion is pseudoscalar, and vector rho is vector mesons. And if we have strange quark, we have K meson, and vector is K star meson. And also eta or phi, and also we have eta prime. Here, this is a result of the 2 plus 1 flavor QCD. That means up and down quark mass is equal. In reality, they have small difference, but in this calculation, we take they are equal, that is by hand, and also introduce heavy strange quarks. So we call this 2 plus 1 flavor QCD, taking chiral extrapolation and continuum extrapolation. And we need 3 input because we have 3 parameters: gauge coupling constant, and up and down quark mass, and strange quark mass. And we fix these parameters using pi, k, and pi meson mass, k meson mass, Gz baryon mass. Then other prediction. So red symbol is a prediction, and the vertical lines experimental value. As you can see, an agreement between Lattice QCD and experiment are rather good. But of course, these rho or K star or delta, other meson and baryon are not stable against QCD interaction. So it's indeed resonance. Therefore, they have some ambiguity. It's so-called width of these particles. But within that ambiguity, agreement is very good. But now people made further refinement, including isospin breaking effect. Isospin breaking effect means introduce difference between up and down quark mass, and also QED effect, because QED coupling is different from up quark and down quark. So up quark has coupling charge is 2/3, but down quark is minus 1/3. And this is a result of such a calculation, and people introduce up quark, down quark, strange quark, and also charm quark. So it's 4 flavor, 1 plus 1 plus 1 plus 1 flavor QCD. And the QED part, people uses so-called non-compact QED to consider QED interaction. So this figure shows first one is mass difference between nucleon and proton, neutron and proton. This is positive about 1.2 or something in experimental value, but Lattice QCD prediction is 1.5 MeV. And because of the simulation, we can separate QCD effect, which coming from up and down quark mass, and QED effect, which coming from coupling. So QCD effect, quark mass difference gives positive contribution to mass difference. That means neutron is heavier than proton. But QED interaction, because proton is charged, proton is heavier for the QED interaction. Because of the cancellation, we get 1.5. Remember, the nuclear mass is about 1 GeV, or 1,000 MeV. This is about 1 MeV. It's smaller than 0.2%. So as you can see, precision of this calculation like this. Of course, it's almost numerical error plus some systematic error, but we are not so sure all systematic error are included, but still this agreement is excellent. And also we can compare sigma meson mass difference and Gaussian meson difference or D meson or etc. And some of them are prediction, like this one is prediction, I think. And this one is also prediction. And after prediction, some experimental value is obtained. And you can see some very good agreement. And there is no experimental here. This is so-called some rules. And also, this is very satisfied. I think this is a state of art of Hadron mass calculation so far. This was 2015 by BMW collaboration. Same collaboration producing this result.
Excuse me.
Could you say something about this non-compact aspect of the QED? How does that come in again?
Non-compact means instead of using link variable U, they just use since it's U1, it's very simple. We just use sorry. Instead of bracket action, people just use this continuum action on the lattice. Only for U1 case, we can keep gauge invariance of this form. In this case, there is no self-interaction of photons. So it's free photon coupled to quarks. But problem is people believe QED is trivial theory in the continuum limit. Therefore, it's kind of effective theory. And in that sense, it's hybrid between Lattice QCD and the effective QED interaction.
Thank you. Yeah, that's clear.
Can I ask a question?
Yeah.
So how can you obtain the raw metal mass in a standard manner, even if it is just a resonance in reality?
Yeah. Honestly speaking, in this case, it's people measure the two just as before, just calculate 2-point function and the exact mass. But if pion mass is not so light, they cannot decay. But the problem is if pion mass is too light, they can decay to low can decay to 2 pions.
Yes.
But in this calculation, people ignore such an effect.
So the pion mass is not light enough?
No. I think in this calculation, pion can low can decay. But because of some, it's in some sense it's not rigorous calculation, and actually people calculate law as a resonance using different methods. I will explain in the next session.
Okay, okay, thank you very much.
So no other questions? Now some challenge. This is Hadron interactions, and it is approach to nuclear physics from Lattice QCD. So the famous example of the Hadron interaction is a nuclear force. This is a meson theory, and before inventing quarks. 1935, Hideki Yukawa, this is the first director of our institute, explains nuclear interaction by the exchange of the virtual particle. And the interaction range is proportional to the inverse of the virtual particle's mass due to the uncertainty principle. And he predicts that the virtual particles are heavier than the electrons, but lighter than nucleons. And he said it's mesons. And nowadays, we know it's pi mesons. So Coulomb potential is explained by the photon exchange, and we obtain Coulomb potential. But for the nuclear force, pion exchange explain this kind of potential. We call it Yukawa potential. But after the Yukawa, experimentalist reveals the complicated nature of the nuclear force. This is the shape of the nuclear potential. So this vertical axis is the distance between nucleons. And for the long range, one pion exchange dominate, and we obtain Yukawa potential. But at intermediate range, multi-pion exchange or heavy meson exchange produce stronger attraction than one pion exchange. But that potential, attractive potential turn into repulsion at some intermediate distance and become very strong repulsion, which is called repulsive core. So this is a modern understanding of the nuclear potential. And if we would like to calculate nuclear force in Lattice QCD, it's much more difficult than Hadron mass because its process is more complicated. Like if we have proton and neutron, which propagate like this complicated interaction, and then exchange pion sometimes. And pion also has to exchange a lot of gluon like this. And there is a standard method, which is Lucia's finite volume method for the phase shift. And suppose we put two particles in a finite box, and then measure the energy. And due to the interaction, on the finite box, if there is no interaction, we know its momentum is quantized. 2 pi divided by L times some integer. However, because of the interaction, this momentum is different from free cases. And from this difference, we can extract phase shift using so-called Lucia's finite volume formula. For example, for the S-wave scattering, the phase shift is delta 0 k, is k cotangent delta can be expressed by this zeta 0, 0. This is so-called generalized zeta function defined by this sum. So it's three-dimensional zeta function-like function. And Q is difference between integer and momentum. So from this, if we measure energy on the finite box and obtain K and converted K to Q, and plug into this Q into this general zeta function, we can obtain phase shift at this K. So this is a so-called Lucia's finite volume method. But our strategy is a little bit different. So we may ask, can we calculate nuclear potential from Lattice QCD instead of just obtaining phase shift. But problem is the following question. What are the potential in quantum field theory, such as QCD? And important point is potential themselves cannot be directly measured. And this quantity is scheme dependent. And actually, we know similar example in QCD. It is running coupling constant. Running coupling constant is not observable and scheme dependent quantity. So potential is similar things. And suppose we obtain phase shift by experiment, and people convert this information to in terms of the potential, like inverse scattering way. So we obtain potential as I showed before. But in this case, potential is not unique. As you can see, different groups obtain different potential from same data. However, like running coupling constant, it's useful to understand physics, as I said before, one pion exchange, attraction, and repulsive core, or something like that, like asymptotic freedom of running coupling constant. Therefore, potentials are useful tools to extract observables such as scattering phase shift. One may adopt a convenient definition of potential as long as they reproduce physical observable correctly. So let me explain potential method. So we take some condition. So let's consider so-called elastic scattering. Nn goes to Nn. But elastic means there is no other process. Nn go to Nn plus others like pion or N by N or etc. So no particle production at all. So we consider the energy of nucleon is omega k, which must be smaller than 2 nucleon mass plus pion mass. So this is so-called elastic threshold. So we have 2 nucleons and momentum k and minus k. And also we assume the QCD interaction are short range, no Coulomb-like massless excitation. So that means no massless particle exist. And there is a mass energy gap exists between channels. This is equivalent to the Cray millennium problem with the Young-Mills and mass gap. But this is assumption. Also, if we consider unitarity of the S matrix, then S matrix below this threshold can be written in this way: S is equal to exponential 2i delta. This is the phase of the S matrix. So let me explain our strategy. First, step 1, we define so-called equal time number-based salpeter wave function. So this is QCD eigenstate, has 2 nuclear eigenstate with energy omega k. And we consider 2 nuclear operator point x and point x plus r. Time is just take 0. So equal time means they have equal time. And this must be function of the r. And also some momentum k, energy k, or something like that. So we define this quantity. Of course, to define this quantity, we have to give the nuclear operator. Nuclear operator is made of 3 quarks. And this choice, there are a lot of variety, but we assume this, we take local nuclear operator. So that local means quark has same x here. So this corresponding to the scheme. And if we consider some finite box, but if box size is very large, at very large R, that means 2 nucleons separated, very largely separated, then there is no interaction. In that case, this phi kr behave like free wave. So if you consider angular momentum L, then it behave kr, sine kr divided by kr. but we have some phase shift or some delta LK. Important things is this delta K and this phase of the S matrix is same. We can show this is equal. And also we can also show this behavior. That is very important things. Therefore, NBS wave function at given energy is something like scattering wave function in quantum mechanics. And from that, we can obtain information of the scattering phase shift.
Sinya, could you repeat what this KET and NWK is? Is
this one?
Yeah.
This is a QCD eigenstate. This is vacuum. This is the operator.
Eigenstate of what? So you say
the QCD Hamiltonian. Yeah.
You say there are two ends, but does it mean that you have 6 quarks or?
Yeah, two. So it's QCD eigenstate with baryon number 2 or quark number 6.
Quark number 6. So
of course,
so you don't assume that there are 2 nucleus, or you simply have 6 quarks and they do whatever.
Some eigenstate of same quantum number.
Yeah. Oh, okay. And you can sort of pick from this state. You are sort of pulling out the configuration where there are 2 nucleus.
Yeah, but of course this is we cannot obtain such a quantity, but we know such a state exists. And we assume this behavior. We assume this quantity. And important point is if R is large, and because of the short range nature of QCD interaction, this behaves a free wave function of some Hamiltonian, free Hamiltonian. And but in interaction information appear as a phase shift of this wave function. That sounds miracle, but we can show this. So this quantity is very important.
You mean you can show this theoretically?
Yeah, of course, theoretically in my standard. Not completely rigorous. We assume something, but of course, this behavior is up to exponentially small correction.
And what is WK?
WK is energy of the state. So it's this one. WK is energy of this state. So energy eigenvalue of the QCD Hamiltonian. Then step 2 is we define non-local but energy independent potential from this equation. So we know we have n-base wave function, and we know k square because we know k, and this is a free Hamiltonian, and this quantity usually becomes non-zero due to the interaction, and we parameterize this interaction with the interaction kernel uxy. This is a non-local potential, so integrated over y like this. So it's differential integral equation, but we define potential from this equation. And important point, by construction, this uxy gives a correct phase shift because the phi is a solution of this equation. Therefore, if we use this potential and use solve Schrödinger equation, we obtain correct phase shift. Of course, problems, this equation does not fix a non-local potential uniquely due to the restriction of the energy, because we only consider energy smaller than threshold. So we have to give the definition or scheme of the potential explicitly to extract this one. And we here introduce scheme to fix the potential completely using the derivative expansion. So this is integral non-local potential, but non-locality can be expressed by derivative like this. So NN case, we have this kind of expansion. So we have 3 local terms, central part, spin-dependent part, tensor forces. Tensor force is given by this because of the spin. And next reading order term is L dot S part, and also higher order term. And please remember, in this case, we don't use any non-relativistic approximation. We just take some specific equal time scheme frames. In this case, there is no time derivative. Therefore, we have this space derivative only here, delta square here. Then we obtain approximated potential from this expansion. For example, the leading order potential is just simply given by this equation. And once we obtain potential, we solve Schrödinger equation in the infinite volume and obtain phase shift or binding energy below inelastic threshold. And also we can check a size of the error for the leading order potential in the expansion. For example, suppose we consider any wave function is very low energy, just 0 energy, and obtain the potential, and calculate a scattering phase shift. By definition, we can obtain exact result here but some approximation, red line. But instead, we can also calculate potential from energy at very high energy, like very close to the threshold energy. In this case, this result is exact, but blue line is approximation. But we can compare this and check how large is the error in our low energy potential obtained from this wave function. And also by combining 2 wave functions, we can obtain next leading order potential like this. And from this potential, we can calculate scattering phase shift. And we know this result and this result is exact. And in between the approximation. But we think this approximation is not so bad because we have 2 anchors in our calculation. Actually, we can play with this idea using some quantum mechanical potential, so-called separable potential like this. And the potential is given by this exponential function, product of the exponential function. This is highly non-local. And we can solve this exactly, and we obtain a wave function and assess some range R and the free wave function x larger than R. And we can, using our method, we can obtain leading order potential and next leading order potential. So this is some demonstration, and blue line's exact result. And the red line is potential obtained at low energy, 0 energy potential, and we obtain exact result here and very good result up to this point, but we see some deviation. And green one is also obtained from very high energy wave function. So this gives exact result here, but these are approximation. Sorry, the leading order one is orange. But by combining 2 wave function, we can obtain NLO potential and calculate scattering phase shift like this, and which gives the rather good approximation of the exact result.
Excuse me, what does NLO stand?
NLO means next leading order, means this one. So leading order potential is completely local potential, but NLO potential means local potential plus nabla square term in the potential term. So since we have 2 input, we can determine 2 terms, and using this potential, we can solve Schrödinger equation and calculate scattering phase shift like this.
Thank you.
Yeah, so maybe because of time limitation, I just go to
Yeah,
my final
it's
result.
already Wednesday.
Yeah. So as I said before, we cannot obtain NBS wave function directly. And when we use some lattice technique to extract this one. So we have to calculate 4-point function. So we create two nucleon states using some operator J, and we consider NX and NX plus R. And as before, we put complete reset. Therefore, this 4-point function is sum of NBS wave function with some coefficient and some exponential decay. If T is very large, we can obtain leading lowest energy NBS wave function. But to make T very large is result become very noisy and also not so easy for two nucleon cases. Therefore, we invented so-called improved method. So let's consider sum of the NBS wave function and divided by two nucleon propagator square, nucleon propagator square. Therefore, it's sum of NBS wave function with some exponential factor, which is energy minus 2 nucleon mass. So it's sum of NBS wave function, but this NBS wave function controlled by same potential V, non-local potential V. However, this depend on different Kn. So each NBS function satisfies this equation. And problem is we don't know this W0, W1, and we don't know this wave function. So what we know is this R. However, important point is this delta Wn is equal to Kn square and delta Wn square. You can easily check this identity using this form. Therefore, without knowing each term, but what we know is this exponential decay factor T. Therefore, take time derivative, we obtain this Wn. Time derivative of 2-time derivative, we can obtain Wn square. Then remaining is K square, but K squares must be equal to H0 plus V. So we can replace this part is H0 plus V. Therefore, so that this formula tells, without knowing each term from R, we can obtain information of the potential. So we use not only the time space derivative H0, but also using time derivative of T in Euclidean time. So this is a result. So we first order term, first term is written in red. Of course, this right-hand side is non-local potential, but we approximate leading order potential, and we plotted this leading order potential. So first term coming from H0, which gives this red shape, and second term is first time derivative, it is blue one. And also third term, this is relativist correction, which is very small, negligible. And in total, we obtain this the magenta curve. Of course, if we only have one state, this time derivative becomes constant. But as you can see, this second term is not constant. That means there are many states inside in this R. But even if we have many states, we can extract some information. So maybe because of time, I skip some technical issues. And this is a result of our potential. This is some lattice spacing, some box size, but biomass is rather heavy, 700 MeV. And this is red line, red point is our data. And you can see qualitative feature of NN potential are reproduced, like attraction and long and medium range attraction and repulsive quark. And you can compare this phenomenological NN potential. And using this potential, we can calculate scattering phase shift. This is result from this potential. And this is experimental value. But shape is reasonable, but of course, strength of the attraction at low energy is still weaker than experimental value. Because we use pion mass 700 MeV, and that is the reason why strength is weaker. But we are now calculating NN potential at 140 MeV pion mass, but it's very difficult. It's very noisy, and we cannot get such a nice result. But we are working on such a direction. So let me summarize. Lattice QCD is a very powerful method to investigate dynamics of quarks. Not only hadron mass, but also hadron interaction can be investigated from the first principle. The potential method is new, but very useful to investigate not only the nuclear force, but also general baryonic interaction in QCD. The method can be easily applied also to meson-baryon and meson-meson interaction. So our strategy to the nuclear physics is as follows. We calculate potential from lattice QCD and give that potential to the nuclear physicist, and they calculate nucleus. And using that information, we may attack neutron stars or supernova explosion. And in last slide, let me emphasize our viewpoint on the potential in QCD. Since QCD is gapped quantum field theory, then with energy threshold, that is equivalent quantum mechanical description in terms of non-local potential for stable particle. So for example, n bar pi, this is a stable particle in QCD side or quantum mechanical description. So resonance, Nishimura-san asked, resonance can be appear like delta and rho from n pi interaction or pi interaction. And also deuteron appears as a bound state, which is a bound state of the NN nuclear potential. And this is the name of our collaboration. Our name of our collaboration is HAL-QCD collaboration. So it's coming from hadron to atomic nuclei from Lattice QCD. Of course, HAL means famous film, I think 2000 Space Odyssey of 2001 or something like that. Thank you for listening.
Thank you, Sinya, for the beautiful talk. I mean, you've done a beautiful job summarizing all this. Yeah, that's wonderful. So we have asked many questions during the talk, but do you have any questions? Yeah, please don't hesitate to ask.
Excuse me. So you said that your potential you extract from this method is scheme dependent. So
yes,
is it something that should agree with the experimental data in the chiral limit or continuum limit?
Yeah, but as I demonstrated, scheme dependence means, yeah, for example, here, we know potential is this one in this case, but our potential is not this one. It's some local potential with derivative expansion.
Yes.
And as you can see, that gives some exact answer. Maybe it's better to hear exact answer at some point. And in between is approximation. So if we have more and more information, we can get more and more accurate result.
I see.
So scheme dependent, but we can get some anchor at some point.
So ideally, you can obtain something that you can compare really with the experiment.
Yes. Actually, such a kind of comparison is already made with LHC data.
Okay.
Hyperon interaction.
Thank you very much.
Any other questions? But related to this point, you said that your pion mass is still too heavy.
Yeah.
To compare this,
yeah.
But and what is probably, of course, it must be difficult. But is the difficulty something of practical nature, or is there any essential difficulty?
I think practical nature.
Mhm.
But now we are calculating 140 MeV pion mass, and we can obtain nuclear potential. But problem is still very noisy. And so, but for example, if we consider other hadron, so for example, omega potential, it's very clean. And for example, we can predict there exists bound state of 2 omega. And now people try to confirm by that prediction by experiment.
Oh, so omega is something I don't, something strange. Okay.
Yeah, omega is 3 strange quark mass.
Okay. Oh,
We
but they
call
can
most,
do.
yeah, this one, this guy.
Oh, very strange. Can they do experiment using?
Yeah, it's LHC. It's omega is difficult, but we calculate, for example, n omega potential we can calculate, and we also predict n omega may have bound state, and n omega could be detected by LHC experiment. But they invent some funny technique to investigate. It's not scattering experiment. It's heavy ion collision and observe leftover after the heavy ion collision. It's maybe too technical. So
particle physics. Good.
Particle physics, yes.
Any more questions?
I have a question. How do you cope with the doubling problem?
A doubling problem, we in this calculation, we use so-called Wilson fermion. So we put term which remove doubling, but problem is breaks chiral symmetry explicitly. And only chiral symmetry recover in the continuum limit. So we have to eventually have to take continuum limit. But this calculation, for example, they use this Wilson fermion and take continuum limit and obtain this kind of result.
And another question, can you compute the decay rate of the lifetime of a particle?
Which weak decay is depend. Weak decay case, we can calculate some matrix element and convert it to some decay rate, but not all decay rate. But we can calculate some decay matrix elements. Or for example, K meson decay to 2 pi. Such a matrix element can be calculated, and we can convert it to decay rate. But it's also very tough calculation, but possible.
Yeah, so there is no, because masses are calculated directly.
Yes.
And decay rates indirectly.
Yeah, indirectly from using this matrix element. Okay. Not this way, but using some operator and some state, and maybe K meson here, some decay operator here, and the 2 pion state here, and calculate such a matrix element using this kind of technique. But we have many difficulty to obtain such a matrix element. But in principle, it's possible.
And another question: what is NBS wave function?
Sorry, I forget. It's non-beta sulfator. It's name of the people.
Ah, okay. But okay, what is its definition?
Definition is this, and so pick up some eigenstate of Hamiltonian and put it to, in this case, to operator n at x, n at x plus r. So it's function of r. It's behave like wave function of the quantum mechanics. Therefore, we call it NBS wave function.
Okay.
Important property is this property. These guys behave like free quantum mechanical wave with information of the scattering phase shift. But it's only true in QCD or maybe gapped theory. Yeah.
And X and R, these are 4-dimensional vectors or
three-dimensional.
three-dimensional? Okay.
This 3-dimensional this time, but this
Okay.
X is 4-dimensional. Sorry.
So time is put to 0 in both operators.
Yeah, it's equal time. Yeah, so this is the name of equal time.
So
non-equal time
you
is also possible. Yeah.
So do you consider the different times?
Yeah, it's also constant non-equal time case. It's one of the scheme to define a wave function or potential.
Thank you.
Hey, thank you. Any other questions? Okay, so if not, let's thank Sinya for the beautiful talk. Thank you.
Thank you.